Good afternoon, everyone. I am Sneha Ghoshal, fourth year ECE student at Techno India Main, Salt Lake. My project is on field effect transistor based sensor. We all know that the sensor is everywhere. So, through this presentation, we will know about this project.
I am Sayan Mondal. I am a student of EC BTech from Techno Main, Salt Lake. My university roll number is 1300032292 and my registration number is 221300110655. I am a member of major project group number 31. And
Good afternoon, respected sir and ma'am. I am Nisha Kumari speaking. I am final year student, Technomen Salt Lake, EC department. I will be presenting my project, field effect transistor based sensor. So proceeding with the main content.
Good afternoon, respected ma'am and sir. I am Sana Bhadra from Electronics and Communication department, and today I will be explaining the introduction and the working principle of my final year project, which is based on field effect transistor based sensor. So commencing with my further details. Our project is based on field effect transistor based sensor. So FET is a semiconductor device that controls the flow of current using an electric field. So normally FET is used as an electric switch or as an amplifier. However, in sensor technology, the FET or this is used to detect the changes in physical environment and biological environment. Is FET the thing which we have actually used here? It's known as ion sensitive field effective transistor. This is almost equivalent to what MOSFET is, but the only difference is MOSFET has got a metal gate, whereas in ISFET the metal gate is replaced by an electrolyte solution and a reference electrode. Now, the electrolyte solution is basically the liquid whose pH is to be measured, and while the reference electrode is used to provide the reference voltage for an accurate measurement. Now what happens is the pH of the ion solution changes, which actually results in the change in concentration of the H plus ions. Now the ions actually interact with the sensitive surface of the ISFET, which actually changes the electric field. So now, as the electric field is getting changed, it results in change in threshold voltage. Now, while the threshold voltage is getting changed, the drain current also changes. Now, by measuring the change in the current, the sensor actually determines the pH value. So here we can understand that how a ISFET is actually helping us to convert a chemical signal into an electrical signal. So this is the basic working principle of our project. So now my other team members will explain the other parts of the project. So commencing with the other parts of the project.
Literature survey shows that pH sensors are widely used in biomedical, environmental, agricultural, food and pharmaceutical applications. Previous studies have improved pH sensing using ISFET, EGFET, JLFET, silicon nanowire FET and TFET technologies. Among these, TFETs offer low power consumption, low sub-threshold swing and high on-off current ratio, making them suitable for highly sensitive biosensors. Researchers have also proposed advanced TFET structures such as L-shaped, U-shaped, V-shaped and gate-all-around TFETs to overcome the low on current of conventional TFETs. The literature indicates that L-shaped TFETs provide better tunneling efficiency, higher on current and improved pH sensing performance. From the findings from the literature survey, the project objectives are to design a high sensitivity L-shaped TFET based pH sensor, to improve voltage sensitivity and transfer characteristics, to enhance tunneling efficiency using silicon germanium pocket engineering and high temperature gate dielectric, to study the effect of germanium mole fraction, dielectric constant and temperature on sensor performance, to develop a low power fast response and highly accurate pH sensing device from practical applications.
Okay, so this is device structure of our project, and this figure shows the cross-sectional view of the process of silicon germanium pocket and germanium pocket L-shaped field effect transistor, that's mean LTFET based pH sensor, and first that's yellow portion is P plus silicon source. That's mean actually on the left side we have a heavily doped p-type silicon source. This region acts as the carrier injection region, and in the TFET mean tunnel field effect transistor, in a TFET carrier tunnel from the source to the channel through the band-to-band tunneling mechanism. And the second purple portion is silicon germanium pocket or germanium pocket. Between the source and the channel we introduced a silicon germanium pocket or germanium pocket. This is the main novelty of our work, and we selected germanium and silicon germanium because they have a lower band gap and higher carrier mobility than silicon. As a result, we get the tunneling barrier becomes smaller, the band-to-band tunneling probability increases, and the device achieves higher drain current and better pH sensitivity also. From the silicon germanium pocket, we further optimized the germanium mole fraction using silicon 90% germanium 10%, then silicon 80% germanium 20%, and then silicon 70% germanium 30% to determine the optimum composition. And third, that's red portion is L-shaped channel. Why we used L-shaped channel? Because the L-shaped channel geometrically increases the tunneling area and provides the stronger electrostatic control over the source channel junction. This enhances carrier tunneling and improves the overall sensing performance. And then that yellow portion is HFO2 gate oxide. Above the channel we used HFO2 gate oxide because since HFO2 is a high K dielectric material and it provides the stronger gate coupling, improves the channel control and increases the sensitivity of sensor. Okay, then this portion is electrolyte. That above portion is electrolyte portion, and because the electrolyte is placed directly above the gate oxide, and when the pH value changes, the ion concentration in the electrolyte also changes. This is the main, and this modifies the surface potential at the gate oxide electrolyte interface, which changes the tunneling probability and consequently the drain current. Also one thing that changes in electrical characteristics is used to detect pH value. Okay, and then that's blue part is N plus silicon drain, and on the this is on the right side. On the side we have heavily doped N type silicon drain, which collects the carriers after they tunnel through the channel. Then P type silicon body under the L-shaped channel. This channel is fabricated on the P type silicon body, which serves as the main semiconductor region supporting the L-shaped channel. And then the box means Wurite oxide layer. The box layer electrically isolates the active device from the substrate, reducing leakage current and minimizing parasitic effects. And then in silicon substrate actually which provides the mechanical support for the structure. Okay, pH value calculation, that's mean it is simply the process of determining the values of pH that we used for writing the code. And first one is this is the reference paper from where we collected the data to determine the remaining values. And from paper we take this hydrogen P is H plus is equal to P, that's concentration of hydrogen ion, and then concentration of hydroxide ion is equal to N. And from the paper we take P is equal to NV E to the power minus E by EV by KT, and this is the full constant E to the power minus EF by KB by EF minus KB by KT. This is a full constant. For this we can from this we can write P constant with NV. As P constant with NV, then we can write NV constant with H plus, because H plus is equal to P. And also we can write from NC constant with H minus. And from after this we did the ratio, we using the ratio method. Ratio method means tomorrow I have 5 apples and today I have 10. Yesterday I have 5 apples and today I have 10 apples. That's mean the ratio method is 10 by 5 is equal to 2. That's mean the known value plus proportionally is equal to unknown value. So the NV here, the NV pH means unknown value and NV7 is known value. So from here we can write H plus pH by H plus 7 is equal to minus 10 to the power minus pH by 10 to the power 7. From here we calculate the NV's value, and NC's value. NV's value is equal to 2.33 into 10 to the power 26 into 10 to the power 7 minus pH, and NC is equal to 2.33 into 10 to the power 26 into 10 to the power pH minus 7. After this we run this program with this value, and then we get the result. The result is, the first one is the transfer characteristics. The first analysis was the transfer characteristics. From the graph we observed that the drain current increases with increasing germanium concentration. This happens because increasing the germanium content reduces the effective band gap and enhance the band to band tunneling process and improves carrier transport. So among the three composition, the silicon 17 and germanium 30 जो composition है ना, that's exhibited the highest on current and the best electrical performance. After that's the sensitivity analysis. Next we analyzed the voltage sensitivity. The sensitivity increased the approximately 49 per pH for silicon 90 and germanium 10 to and 60 millivolt per pH for silicon 80, germanium 20, and finally 62 for silicon 70 with germanium 30. This confirms that the higher germanium concentration enhances the tunneling probability, which results in greater current variation with pH and therefore the higher sensitivity. And then pH characteristics. After selecting the optimized device, we analyzed its pH sensing characteristics. The pH value from 1 to 14. As the pH increased, the transfer current shifted toward higher gate voltage, and this shifts occurs because the changes in pH modifies the surface potential at the electrolyte gate oxide interface, which changes the tunneling probability and the drain current. And then the effect of dielectric constant. The high K dielectric materials such as HFO2 and PiO2 provide stronger electrostatic coupling. So wait. this one. As a result, the gate has better control over the tunneling junction, leading to stronger band bending and higher sensitivity. Among all investigated, the dielectric materials TiO2 produced the highest sensitivity. And if I said about temperature analysis, we also studied the effect of temperature from 100K to 500K. As the temperature increased, the semiconductor band gap also decreased, which further enhanced the band-to-band tunneling process. Consequently, the sensor's sensitivity increased with temperature. If we say about comparative study, then finally we compared 4 different structures. One is silicon source L-tunnel field, one is germanium source L-tunnel field, and the second is silicon source with the germanium pocket, and fourth is silicon germanium source with silicon source with silicon germanium pocket. This comparison clearly shows that pocket energizing significantly improves the sensing performance. Among all the investigated the structure, the silicon germanium L-tunnel field achieved the best balance between electrical performance and pH sensitivity. Actually, germanium performs best, but in 500 temperature, silicon germanium performs best because germanium cannot go in the high temperature.
Now I will explain performance comparison of different sensor device. This table compare different FET-based pH sensor based their voltage sensitivity, which measure millivolt per pH. This comparison is mainly taken from the previous research paper. In adding, we included the silicon LTFET and germanium LTFET sensor at 300 Kelvin in our comparison to provide the best, more complete performance. Now I would like to conclude my presentation. In this work, we successfully designed and analyzed to the Silvaco TCAT simulation software. The use of pocket engineering significantly enhanced band-to-band tunneling, which improved the electrical characteristics. The optimized is silicon 0.7 and germanium is 0.3 pocket. Composition provide the best balance between on current and pH sensitivity. In addition, using high Kelvin gate dielectric material and HFO2 and TiO2 improve electrostatic. The temperature analysis also show that proposed sensor maintain sensing performing with temperature range. Therefore, the purpose device is promising candidate for next generation low power high sensitivity pH sensing application.